Why did the stream finish? Okay. Now, hard to tell what's happening. You do back on. Oh, bugger. It's hard to tell what's going on. This. Okay. Well, this is annoying. I hope this would work better. Um, Live, determining quality. Just pause these. Sorry about the preview, I guess. Okay, I'm gonna change the slide just to see if I can get some type of update. Okay, well, welcome to the stream. This has gone a little bit awkward. I'm trying to get a new streaming tool to work, and I think I screwed it up, and I can't tell what tool is actually updating correctly. No. Oh, this is annoying. Well, if anyone want to say time, so Twitch stream is fine. Okay, so let's see. Hello. That popped on upon everything. Let me see. Yeah, I guess I just need to trust the tools. Let's go check out my events. Events. Okay, I guess we're just going to... The tool created a bunch of new events. So just that into this one, I guess. Okay, we're just gonna trust that this is moving forward. And I'm sorry for the redundant events. Let me go clean that up real quick. Going to clean that up. Give me a. We're gonna delete the old event. Five. Okay, yeah, we're just to ever. So I'm gonna assume the services are going okay, and that me just grabbing all these back over and over is just messing up things. So let's move back down to this slide. Okay, everything says it's healthy. We're just going to stop using so many of the tools. Okay, we'll call this good. Okay, welcome to the stream. It took us 10 minutes to figure out all our little issues. I'm going to try to keep track of everything in the chat window. So this is FPGA Zealot. We're going to go over the Raspberry Pi 240, the RP2040, and the Spartan 7 FPGA. Sorry, playing around with the new tools. Guess I'm just going to have to trust that it's working. And that everything is being sent well enough. Okay. So today, this is not a sponsored live stream. Let me fix that. This is not sponsored live stream. I'm not played by AMD. Yep. This content is my own, so let's not worry about. I don't offer official support. These opinions are on my own. And today we wanted to look at this board and why I try to do IT on the stream. Go a little bit in the corner here. We're going to play around with this Spartan 7 and RP2040 board. And what we're going to be focusing on is that there's 10 pins between the 240 and the FPGA. And I'm going to open it quick here. And I want to get the RP2040 up, talk about that. And this is a board from Adiuvo. This is a company that Adam Taylor runs out of the UK, and this is one of their development platforms. It's a really interesting one because it has the RP2040, which kind of acts as like an IO, I guess, a small dual core ARM processor with some interesting IO. And we can pull up the data sheet. This is one. Yeah. So we can look at what the RP2040 is. The RP2040 processors really shown on here, are they? Fabric peripherals. Oh, here's the processors. have two processors, and we are going to be looking at the GPIO. We're first probably going to look at the very generic GPIO, and then I want to look at the PIO, the programmable IO, I believe, that can do really cool things. What do they call the PIO in here? Where do they go into? Right here. So we have different state machines, and we can do fancy things with the IO. Is a lot more complex. I really need to read more into how this system works so we can get able. We can maybe look into it a little bit more as we go. But this is kind of the interface I want to communicate between the processor and the FPGA. There's a very basic user guide that comes with it that helps you bring up the FPGA and the processor. We're probably just going to jump into how I am going to play around with the Raspberry Pi, the 240 talking to the FPGA. Trying to see where the example designs go. Okay, let me go grab the link. Okay, so yeah. There's a repository that has all the various user guide, the board definition, application examples for this board. And we bring up the board in Vivado. So I did a very basic design where we take the system clock, we up it to 200 megahertz, and we have a system ILA that's looking at the 10 pins coming from the RP2040. And if we look at the utilization for this, we are using almost all of the almost 80% of the LUTs, and I guess we look at this, we're using about almost 3,000 LUTs and about half the VRAMs to be able to get this. And we are having some negative slack in here as well, so the timing might be off for a few things where that is. But we won't worry about that at the moment. We're just wanting to look at the IO. So if we go here, we can look at the 10 pins that are coming out of the processor. And in the guide, for it, they use a tool, MicroPython. They're using MicroPython to bring the board up. And that's how they're programming the RP2040. So we're going to be using the RP2040 with the Thorny to be able to program it. We had a question in chat about the PIO versus GPIO. That was in YouTube. So we go back to the data sheet. Let's go talk about that real quick. This is killing my bit rate, but that's okay. Stable picture. So we want to talk about the difference between the GPIO and the PIO. So the GPIO are the kind of the pins, and these GPIO pins connect to the various peripherals that are kind of hardened. So all these peripherals right here, the SPI, the pulse width modulation, the UARTs, the I2C, the ADCs, these are all like directly connected to, can be connected to GPIO, and you can kind of configure which pins. So the GPIO blocks like this giant mux that goes between these hardened cores and which pins you want to use. Because the GPIOs aren't specific, so you can connect the UART to any pin. What the PIOs are, they're little state machines. So these are really small little state machines, like really, really small, like processors almost, right? And these little state machines can also connect to the IO. And where the UART has a hardened silicon that's doing very specific timing and whatnot, you can replicate that instruction in these small little state machines. So the PIO are programmable IO that are connected to the GPIO, and they can replicate a lot of the functions here, or you can do unique interfaces here. So it's a really cool system having like a very simple processor that can go through all the different instructions. So I wanted to do a basic GPIO example. And so we're gonna go to Thorny right here, and let me bring this guy to make this full screen as best we can. Let's actually pop it out side like that. So we're gonna put a simple GPIO right here, and what we're gonna do is we're gonna trigger on the rising of the first edge, and now we can see the GPIO. So our sample clock for our, that's fine. Feel free to ask questions and keep the conversation going. So a lot of these GPIO, when they're driven by this processor, it's really slow, right? We have these times. So if we like if we take away the timing, so it's not half a second. Oh, that's just the for statement. Maybe we'll see something better. Okay, so let's do this. I want to, so let's turn a pin off. Let's turn a pin on and immediately turn a pin off, right? So if we turn this into the RP240 and we trigger here, we can see the up and down of each of these things. This is as fast as the processor can go, right? So if you're driving the pins from the software, it's relatively slow. It's about 500 clock cycles of a 200 megahertz clock, which is 2.5 nanoseconds. So 500 times 2.5. So you're looking at probably about a 2.5 nanoseconds times 500. You're looking about a microsecond between driving the different systems. Um, and so it's about probably about 1 to 2 microseconds between the GPIO being driven high and driven low. That's really slow. I mean, it's not terribly slow if you're bit banging like a simple interface with the system, but let's look at what happens if we do a basic PIO system. Let me bring in the PIO example and we can talk about it. Okay, so let's down to one pin. Um, okay, so right here we're programming the state machine. So we're gonna go program the state machine that's in the RP240. So the processor is not driving the pin anymore. We have a very basic state machine. And when we do this, we can see that we are going much faster. And this is happening about so the period is about half of the sample clock, or a little bit less than half. So we're getting about 80 megahertz when we do the when we're doing the, so yeah, about 80 megahertz for when we are doing the PIO. The PIO is really nice to do like these high speed, low level changes on the system. That's where that's coming. Um, but and we can also increase this, right? So if we go back to the example I copied over, we have two IO. So we're basically just driving two of the pins and two of the pins, so they're alternating. And if we, I need to run. Yeah, so we can see that the two pins are now alternating on the system. and that we are running it as fast as possible. I mean, this is cool if we want to do like maybe very basic repeating patterns on these pins, but it's not really useful for an application. For an application, we want to send the data. So I'm using MicroPython. So we're doing MicroPython through Sony to program the RP2040. It's really nice. It's really easy. And also you can use your favorite large language model, LLM, to be able to help you code it. It's really easy at providing some good examples. Except DMA. DMA seems to be a pain. So and let me show you the example of driving. Have the one where I drive all. I guess we could. So let me show you some of the examples. If we go up to like 5 pins, right? We can go 0 1 0 1 and 0 1 0. Now doing 5 pins, the same thing. So we can run this, and we do we know. Sorry. So when I write 6 bits, and a half. Okay. Um. So we can do 5 of the lines at like full rate. When I try to do 6, not sure why this happens, but if I try to do 6, it breaks it. So it can only do like 5 pins per state machine. I need to figure out what. I don't think this is correct. There's probably something I'm missing on the configuration. But what we can do is since we have 4 state machines per PIO, we can just do another PIO, that state machine, and we can drive it to pin 5. And if we do this, we can now drive all 10 lanes. So we can drive all 10 lanes at 80 megahertz, getting us about 80 megabytes worth of data. But this isn't data. This is just us toggling pins. We want to be able to send data across the system. To send data across the system, we can push data into the system, into the state machine. We can do like this SM put. So let me show you the limitations of this. So the main processors are driving this transition. So when we do this, we get every microsecond, right? Because it's like every 500 cycles. Yeah, about every microsecond, we are able to send a single bit of data. And this is us doing it as fast as possible. So it's for the RP2040, the best way to be able to send data across this is to use a DMA transaction. So we need to figure out how we can connect DMA to the PIO, which is possible. I found a few examples. I'm still working on how to do it the best way. You can look at kind of how the DMA works. But we should probably break down the PIO first. So there's different things in the PIO. You have your little assembly that you write for your PIO. So this is what is being driven into the state machine. And we go back to the data sheet for this to drive a little bit more into what the PIO is doing. Because we're doing like direction, that pin, control flow. So this is providing a C example. It's not really good MicroPython examples. For example, the stream data through the output pin rate of 1 byte per 2 clock. Moves a 3 different type. Place it into instructions, shift the data from to other desks at a time. automatic refill the FIFO on an out instruction is reached. So we're like shifting in 8 bits of data at a time. So this is doing auto pull, where we're just okay, so we can do programming wrapping allows for this information into the output of every stream system clock cycle. So yeah, I need to read through this and maybe provide some better examples of how we can work on this through via out and set. There's like a secondary thing as well. I had some better. Okay, here's where the instructions are actually useful. Instruction set. Okay, here we go. We have out, we have set, we have push, we have pull. Then we can go in and talk about what each of these things are actually doing. And so for doing the set command right here, pins, oh, only 5 at a time. We can only send 5 bits. Okay, that's why the other one's breaking. We can't send more than 5 bits. Approximate data. Okay, that's why I can only use 5 bits. Okay, that makes sense. Okay, we have a great question. What we're going to be using for a clock between if we're actually sending data. So if we're actually sending data, how do we synchronize the clock and do handshaking? That is a fun question. As you can see, the suggestion here is that you can use the data. So we can use the out command for data. So we can use the out command for data, but then we can use the set command for a clock. Maybe we did a stall, that would make more sense. Maybe we learned how to stall it. So yes, you could either use a clock or you could use some type of asynchronous handshaking. It also depends if we want to go bi-directional, or how we want to do a bi-directional interface. So you probably want to dedicate one pin to clock and direction. To do clocking between the RP2040 and the FPGA, probably want to dedicate pin for clock in direction. Probably makes the most sense to me. It'd be interesting to kind of set up a bi-directional bus using clock and direction. The only issue is what can we do on the processor that's actually useful for the FPGA? So I guess any comments, any ideas how you would use a RP2040 with an FPGA? I'm thinking control status registers. Try to replace that's a better Oh, that only got sent to them. Okay. So I did find a really interesting example of a video frame. I'm gonna. So this code uses. I found this. I should probably from. This was on GitHub. Let me look at my GitHub hit. We can find out where I got this from. Okay, so this is the Pico code. This as a link. A.py. There we go. And this looks this is rather complicated in how it sets up the different state machines. So back to I'm gonna go ahead and just run it, and we'll see the code right here where it's drawing it. So I'm just gonna have it like continually go through these different systems. So for here we have several different state machines, several different PIO state machines. So we have the H-sync signal, and this is pin 8 right here. That's the H-sync on pin 8. And it's using state machine 0. And then we have the V-sync here, which is going to be on pin 9 using state machine 1. So state machine 0 is driving pin 8. State machine 9 or state machine 1 is driving pin 9. And then down here we have the parallel RGB data, so just one signal per. So we're just going to do one color for RGB, so 3 colors. And this is going to state machine 2, and it's driving pins 0, 1, and 2. And then they have a bunch of DMA that they're configuring here. I really need to figure out how this works better. But then they are setting up pointers to enable the DMA, and they're using this pointer 32 of an H buffer line. Where is this H buffer line? Find. Okay, yeah, here. The DMA has an H buffer line right here, 0.32. Okay, right here. So we have an array, H buffer line, array, long, thing on the visibles. We set this up right here, address. We get the address of the buffer line. We free the memory. We configure the DMA to use this buffer line address. And where do we do the destination of the DMA? Okay, we're going to configure DMA. Channel 1 is data transfer. So setting up the DMA, the number of RGB state machine. Formatting line reading, 32-bit transfer. Channels enabled by config DMA channel. All the fun little things right here listed. Setting up control DMA channel 0 to run channel 1. Vertical visible area lines. So this is exactly sure, but it's also reading has a different read and write address. And then in our RGB signal, we are doing shifting here. And we have auto hold enabled. So it's just going to constantly be shifting that data into the pins using the out base. I'm not sure what the side set does. I need to go figure out more how that works. But we have this label out that it's just constantly jumping between for a frame, I believe. Then we go to the VSync section. Setting up this is a great example. Wish I had a little bit more comments and ways to play through it a little bit better. So there's a bunch of utility functions, and then we set up the system. So here the DMA, we're using about half of the SRAM. And then we have about the other half free. And then we're just drawing incremental pixels here. So if we zoom in on the trigger here, we can see the incrementing values. Shared external oscillator. Okay, so we have some ideas from YouTube about RP2040 functionality. So we have the shared oscillator and shared chunk of memory. Encryption offloading. So could we do like a secure boot up process of encryption, shared memory? It'd be interesting creating a protocol of shared memory between the FPGA. Well, you would want probably want to do like a control line where you're accessing memory map access. So, let's see, you probably want two functions to support applications, right? You want a basic memory map for register read/write. Then you want to and support like direct DMA to and from the RP2040 SRAM. That's how we'd be able to read and write the system. Okay. So I just need to trust. Unfortunately, I don't have a display at the moment. I do have. Okay, put it. So let's show this to the camera. What can we see? So we do have a PMOD video out that we can potentially have the FPGA drive. So we could just send RGB signals over here and drive a DVI over HDMI chip. So that might be something interesting to do with another video where maybe the FPGA handles the low-level control signals and there's like a frame buffer of some type. It has to be a relatively small frame buffer with 1 pixel colors because we can't really do much else with this memory space allocated. There is additional memory. Let me see how much additional memory we have here. We have a 64 megabit on the SD RAM. So maybe we could connect the Raspberry Pi to the FPGA SD RAM. That would probably be really interesting. right? To have the Raspberry Pi be able to maybe write and load things into the SD memory on the FPGA. So I that's probably the most visual thing. So I'll probably look at trying to do like a frame buffer that kind of shares memory between the Raspberry Pi and the FPGA, and maybe figure out a way to like expand colors or something. Kind of fun playing on these small embedded environments. Okay. So this is going to be mostly a short stream. I was trying to figure out the tools. We had a rough start, but I think I just need to um, trust the settings on everything and figure out best way to host things. Let's go see what that previous event was doing. But yeah, feel free to ask some questions. Any ideas of what you would like to see in the future. Um, and I think that's mostly good. So, we're gonna have more live streams coming up in the next 2 weeks. I might put one in between, but on the coming up Tuesday, we're gonna look at the Spartan UltraScale Plus. I want to look at UART, serial, I2C, both different ways you can configure it in the Vivado tools and the Vitus tools, and what's optimal for kind of a small platform. And then we're gonna have another Altair FPGA AI Suite stream in November 11th, looking at uh, AxiStream data, how we can process AxiStream data with their AI IP core. So thank you for joining. I definitely need to figure out more of the streaming system. Um, I think I just don't have the internet bandwidth at the moment to be able to watch all the various streams on all the various platforms. Um, but I think that's mostly good. You want to see? Oh, it's read only in chat. Okay, let's try. Um, does chat. I'm going to try to chat on my own video in LinkedIn to see how it works. Okay. Um, okay, thanks for watching. Sorry, all the event and links were messed up for YouTube and LinkedIn. I think if I trust the system next time, we should be fine. And figure out a way to like monitor. I do wonder. Let me see if I pull up on my phone. That seems to be pretty good on my processing on. Okay, then let's go YouTube. Got my. We can go to YouTube. Like good way to it than Twitch. Okay. Let me check if there's any more chat messages, but I'm probably going to close the stream down. Thank you for watching. Feel free to leave a like, subscribe, whatnot. We'll try to be a little bit more frequent and a little bit more stable, and we do streams and try to keep up with everything. Thank you. Let's see, what's the best way? I'm going to close these down one by one through the tools. See, LinkedIn has gone down. Previously live, okay. So let's view this. YouTube has gone down.